Download this code from codegive.com, link in the description below. Deadlock settings and launch options typically refer to configurations that can be applied to prevent or manage deadlocks in multi-threaded or multi-process applications. However, the term deadlock settings launch options is not standard terminology in programming or computer science. Instead, let's break it down into understanding what deadlocks are, how to prevent them, and provide a code example that highlights best practices for avoiding deadlocks. Understanding deadlocks. A deadlock is a situation in a multi-threaded environment where two or more threads are blocked forever, each waiting for the other to release a resource. This can lead to a situation where none of the threads can proceed, causing the application to hang. Conditions for deadlock. Deadlocks typically occur when the following four conditions hold simultaneously. 1. Mutual exclusion, at least one resource is held in a non-shareable mode. 2. Hold and wait, a thread holding at least one resource is waiting to acquire additional resources. 3. No preemption, resources cannot be forcibly taken from threads holding them. 4. Circular wait, a circular chain of threads exists, where each thread waits for a resource held by the next thread in the chain. Best practices to avoid deadlocks. 1. Lock ordering, always acquire locks in a consistent order across all threads. 2. Timeouts, use timeouts when trying to acquire locks to avoid waiting indefinitely. 3. Avoid nested locks, try to minimize the use of multiple locks at the same time. 4. Use try-lock, instead of blocking indefinitely, use mechanisms that allow you to attempt to acquire a lock without blocking. 5. Resource allocation graph, monitor resource allocation and release to detect potential deadlocks. Code example. Below is a Python example using threading to illustrate how to avoid deadlocks using lock ordering and timeout. Python. Import threading. Import time. Create two locks. Lock _ A equals threading.lock. Lock _ B equals threading.lock. Def thread 1. While true. Try to acquire lock _ A. With lock _ A. Print, thread 1 acquired lock _ A. Time.sleep, 0.1, simulate work. Try to acquire lock _ B. Print, thread 1 trying to acquire lock _ B. If lock _ B dot acquire, timeout equals 1. Try. Print, thread 1 acquired lock _ B. Finally. Lock _ B dot release. Print, thread 1 released lock _ B. Else. Print, thread 1 could not acquire lock _ B, retrying. Def thread 2. While true. Try to acquire lock _ B. With lock _ B. Print, thread 2 acquired lock _ B. Time.sleep, 0.1, simulate work. Try to acquire lock _ A. Print, thread 2 trying to acquire lock _ A. If lock _ A dot acquire, timeout equals 1. Try. Print, thread 2 acquired lock _ A. Finally. Lock _ A dot release. Print, thread 2 released lock _ A. Else. Print, thread 2 could not acquire lock _ A, retrying. Create threads. T1 equals threading.thread, target equals thread 1. T2 equals threading.thread, target equals thread 2. Start threads. T1.start. T2.start. Join threads, in a real application, consider a graceful way to terminate. T1.join. T2.join. Explanation of the code. Locks, two locks, lock _ A and lock _ B, are created. Thread functions, each thread, Thread 1 and Thread 2, tries to acquire locks in a specific order. Timeouts, the acquire, timeout equals 1, method is used to prevent indefinite waiting. If a lock cannot be acquired within the specified timeout, the thread will back off and retry. Locking order, both threads attempt to acquire the locks in a consistent manner, which helps prevent circular wait and thus deadlock. Conclusion: by following best practices such as lock ordering, using timeouts, and avoiding nested locks, you can significantly reduce the risk of deadlocks in your multi-threaded applications. The provided code example demonstrates these principles in action. Always analyze your specific application and environment to identify the best strategies for avoiding deadlocks.